discuss on the how diffusion can be looked at when reaction occurs, just before the reaction, how the diffusion acts. So you have learned about this flow past immersed body. So there you have learned something, but here the how diffusion can be looked at this way. And look at this picture. This sphere is a catalyst sphere, say perfect sphere I have taken. Actually in practice it is the catalyst particles are not always perfect sphere, but for simplicity's sake I have taken it as a perfect sphere, and these are the small pores inside. Anyway, before going to the pore diffusion, we will consider the external diffusional resistance to mass transfer, how external diffusion is acting. And here you see that A is a reactant molecule which is diffusing through a stagnant film of B. So this is a mixture of A and B, where B is stagnant. If we consider B is stagnant, then we do not have to consider the movement of B. So the equation will be more simple. Here species A, which is present in dilute concentration. Another assumption is A is in dilute concentration. If it is in dilute concentration, then bulk movement we can neglect. Only we will consider, we can focus on the diffusional movement of A, and is diffusing at steady state already. Yes. Hello. Anybody is saying anything? No. Okay. Now look here in the picture. Here we have considered many assumptions, and which have made everything very simple. A is in dilute concentration, and which is diffusing at steady state. Already steady state has been reached. That phase we are considering. From the bulk fluid through a stagnant film of B. Another assumption is B is a stagnant, and B is not diffusing, of thickness delta to the external surface of the catalyst. So this is the flow of the A through stagnant body of AB. So just above the catalyst solid surface there is a film of B around, and say A is diffusing through the bulk, from the bulk through the film and coming on the surface of the catalyst, external surface of the catalyst, and the thickness of stagnant film of B around the catalyst surface is delta. Delta is the thickness of B. The concentration of A at the external boundary is CAB. B is the bulk, and at the external catalyst surface is CAS. That means on the surface actually. CA in the bulk and CA on the surface. So CAB is just outside this delta thickness, and CAS is on the catalyst surface. That means at the end of delta. With CAB greater than CAS, obviously in this small thickness delta, there is a resistance acting for B to come on the surface of the catalyst. So due to that resistance, obviously whatever concentration of A is there in the bulk cannot be the same as on the surface of the catalyst. It will be lesser. So lesson, say if A starting point of A is 100 molecules in the bulk, say maybe 50 molecules can reach on the surface of the catalyst, just crossing the boundary layer. So CAB is obviously greater than CAS. That means CAS obviously less than CAB. As the thickness of the hypothetical stagnant film next to the surface is small with regard to the diameter of the catalyst particle, this is another assumption. As catalyst particle, we have considered it is a small catalyst particle, and we have thought that the thickness delta, that means thickness of B, film of B around the catalyst particle is also very thin. What is the assumption then? Hence the curvature is neglected. We have taken a small segment of this film, thickness of delta, which is not curved. This one we have considered. This is a rectangle, perfect rectangle we have considered. The diffusion is considered to occur in rectilinear coordinates. There is no curvature. This small part which we have considered is a perfect rectangle. Next is the determination of the concentration profile and flux of A in the surface. So that rectangle we have taken here. So this is the catalyst particle. Above it there is a delta thickness, this rectangle, where the starting is z. If it is a z coordinate, we have taken z is equal to 0, and this is z is equal to delta, this thickness in this coordinate. And Faz is the molar flow rate of A at the point z, and this is z coordinate. Cab is in the bulk, and after delta thickness, it is Cas on the surface of the catalyst, and Cab is greater than Cas. Now, within this rectangle, where some A is already entered, we have taken another thin section here, whose thickness is dz. And here we have taken at the starting of this small thickness, a small section, it is z, and as this thickness is dz, it is z plus dz. This is small thickness one. So we will do the mole balance of A against this small section. So rate in minus rate out plus rate of formation is equal to rate of accumulation. As there is no formation, no accumulation, because it is not a reaction, it is only the diffusion. So it will be rate in minus rate out is equal to 0. If Faz is the molar flow rate at Z, and Faz plus dz is the molar flow rate at Z plus dz, then considering only diffusion and no reaction, obviously Faz molar flow rate in minus Faz plus dz is molar flow rate out, plus no rate of formation is equal to no rate of accumulation. So dividing by dz, we get Faz plus Faz minus Faz plus dz by dz. If we divide the function factor by dz, is equal to 0. And if we take limit dz tends to 0, we are getting d Faz dz is equal to 0. So this you know. Now, if AC is the area of section dz, say this small section has area AC, then Faz, that means molar flow rate, is equal to diffusional flux, that is, it is mole per second. Waz is the molar flux, that is mole per area second, into area. It will be the same unit wise, mole per second. This is mole per area second into area is mole per second, both sides. Now, instead of this Faz, if we put this Waz AC, it is coming dWaz dz is equal to 0, as AC is constant. This rectangle is area is constant. So this way, from here, from dFaz dz is equal to 0, we are getting dWaz dz is equal to 0. This is flux. Now, we have considered dilute solution and Z direction only. We haven't considered any other direction. And it is dilute concentration. If it is dilute concentration, then bulk motion is neglected. Then we can only say the fixed first law of diffusion, that is WA molar flux is equal to minus DAB dCA dZ. And W, if we differentiate this, dWA dZ is equal to minus DAB d2CA dZ2. Now d2ca dz2 is equal to 0, add as dwa dz is equal to 0. This is 0. In the last slide we have seen dab cannot be 0. So d2ca dz2 is equal to 0. So from here we get, if we integrate it, we are getting dca dz is equal to k1, and again double integrate, ca is equal to k1z plus k2, where k1 and k2 are the integration constants. Now we have to find out the integration constant values by putting the boundary conditions. What are the boundary conditions? Now applying boundary conditions to evaluate the constants at z is equal to 0, ca is equal to cab. Look at z is equal to 0. When z is equal to, if you consider the full one, z is equal to 0, ca is equal to cab. And when z is equal to delta, ca is equal to cas. If z is equal to 0, ca is equal to cab. Now if you write it here, you are getting k2 is equal to cab. If you put z is equal to 0, then this quantity is coming 0. And k2 is equal to cab, because when z is equal to 0, ca is equal to cab. And at z is equal to delta, ca is equal to cas. Then if we put it here, ca is equal to cas plus k1 delta, because z is equal to delta, plus k2. Now k2 value we know, cab. So here, from here we are getting k1 is equal to cas minus cab by delta. So we could get the values of k1 and k2. Now put the values of k1 and k2 in the equation, in this equation, ca is equal to k1z plus k2. It is coming as ca is equal to cas minus cab by delta into z plus cab. And ca is equal to cas minus cab z by delta plus cab. Now if we plot ca, concentration of A, against z by delta, z is that small the element, delta is the thickness. Then if you see the curve, it is a straight line. This way also we can write the equation, ca minus cab by cas minus cab is equal to z by delta. From here we are getting this. Now this is the concentration profile of A. We are getting, plotting ca against z by delta. It is a straight line. Wait, it is a straight line with a negative slope. Why? Because cab is always greater than cas. So if we plot, cab is highest, it is the bulk concentration, and as the diffusion progresses, concentration continuously decreases, and one time may come when z by delta may be 0, where we can write cas. Here also there may be some cas. This is cas. Now when z by delta is equal to 1, then we can write it is as cas. Just a moment. Now determination of molar flux of A diffusing through the stagnant film, dilute solution, and EMCD. There are other conditions also where we can try the molar flux of A. For dilute solution and EMCD, flux is given as only the diffusional flux, WA is equal to minus DAB dCA dZ. Previously we obtained Ca is equal to Cas minus Cab into Z by delta plus Cab. This one we have just received, we have got just now. So putting Ca in 1 in place of Ca here, if we put this value, what it comes? Wa is equal to minus Dab, d of the whole part, this one, by dz. Cab is constant, so it is coming 0. Is equal to Dab, minus sign cancels out, Dab Cab minus Cas by delta, if you differentiate this one. This one is 0, d CAB dz is 0. Now it is coming d CAS minus CAB. If you by delta, this is z, so this z will not come here, and just make this opposite CAB minus CAS, then this minus sign is going out. So it is ultimately coming WA is equal to DAB CAB minus CAS by delta. In terms of mole fraction, if we instead of concentration, if we put mole fraction, then we have to multiply here. Instead of CAB we can write YAB, instead of CAS we can write CYAS, and we have to multiply it by total mole CT0. CT0 is the total mole. Now one example I have given here, just for your information. Say DAB is equal to 10 to the power minus 6 meter square per second. CT0 is equal to 0.1 mole per meter cube. Delta is equal to 10 to the power minus 6 meter. YAB is equal to 0.9 and YAS or YA delta also you can write, whatever you wish. S is surface, delta is at the end of the delta rectangle, is equal to 0.2. Then WA is coming after you solve the equation, this equation, it is coming 0.07 kilomole per meter square second. This is for dilute solution and EMCD. Now for stagnant film, similarly we can solve this. WA is equal to minus DAB DCA DZ, but for stagnant film there should be a bulk movement of A, but B is stagnant, so WB is equal to 0. This part JA plus BA, this BA part is 0 of sorry, B not BA, bulk part is 0 of B, bulk part of B is 0, bulk motion of B is 0, but bulk motion of A is remaining because A is moving. So what is the molar flux of A for stagnant film? This is the diffusional flux plus bulk flux. So this one we can write this way, WA YA minus 1 DAB DCA DZ. If you take this here, so DAB into C is the total concentration, into DYA DZ. We are writing in terms of mole fraction. Or WA, again we are integrating it, 0 to delta DZ is equal to DAB C is then limits are when Z is equal to 0. It was previously CA is equal to CAB. Here as we are considering the mole fraction, so it is it will be YAB instead of CAB. And again it was when Z is equal to delta, CA is equal to CAS or CA delta. So instead of CA, we are writing in terms of mole fraction YA delta into YA by YA minus 1. We are made the fraction of this equation. Now boundary conditions, what I said just now, when Z is equal to delta, YA is equal to YA delta or YAS. When Z is equal to 0, YA is equal to YAB. So it is coming as by solving this equation, we are getting WA into delta is equal to DAB C ln 1 minus Y delta, YA delta by 1 minus YAB. Putting the previous values of the quantities WA, similar way for the stagnant film, if we put the previous values, what we have given here, the same values if we put, and then we are getting WA is equal to 0.208 kilomole per meter square second. Then hence the flow through stagnant film is greater than for dilute solution or EMCD. This is the proof. Why it is more? Because in the stagnant film we are considering the bulk motion also. So there is an extra motion due to the bulk movement along with the diffusional movement. So if we draw the concentration profile, now the above equations, both the equations, dilute solution EMCD and stagnant film, if we plot in a single plot, a single graph, we are getting this one, this type. This is YA, mole fraction, against the Z by delta. Instead of YA, you can write CA also. Similar way you will get. This is dilute solution or EMCD, a straight line with a negative slope as it was previously shown. And stagnant film, it is a this type of curved curve. So this is the concentration profile for different types of diffusion. Now, I have discussed till now about the external diffusion, diffusion of the reactant molecule from the bulk to the catalyst surface.
How do we calculate delta?
Look, it is you cannot calculate delta that way. It is actually it is assumed. It has been done several times with different experimental way, and by assumption and iteration, and then putting the values and see in which the actually diffusional flux is matching. This way we can get. You cannot, it is totally based on assumption and doing several times as you do, several trial and error this way.
So how do we measure the diffusional flux to validate which delta is correct?
Diffusional flux can be actually, look, this one we have considered in a differential area or differential volume. Actually, experimentally, we can determine the diffusional flux for the whole catalyst mass. It is the mole per area time. So from there we can take the single catalyst particle and how many catalyst particles are there in the whole mass of the catalyst bulk, whole bed of the catalyst. From there you can get per particle what is the area, and from there this way you just top down method you can come down. The top values you know, so this way you can just come down slowly. And then you have to assume this is the area, or this is the volume, or this is the thickness, and then you validate, then you can match your the top value with your calculation at the bottom level. This way you can go.
So for delta will vary according to the different catalysts.
Actually, delta, it is an assumption. No? This is the thickness we are taking. Now, obviously, it will vary not only on the depending on the catalyst surface, but also depending on the type of gaseous phase. What reactant you are taking, what is its affinity, and what thickness of boundary layer it may form around a catalyst bed. And it is a complex calculation. In fact, here we have taken everything very simple. You know, if two catalyst particles or three catalyst particles say are arranged together, it will form say a rectangle, a triangle. Now you are not getting the whole catalyst external surface in that way. You are getting the overlapping surface actually. So there are many loops here. There are many complex calculations inside. So this way we are doing the very simplified one. We don't take any overlapping surface. We take a perfect sphere, and actually we have afterwards we will see that we don't take in fact a perfect sphere. What we do, we have assumed a circular picture. of every catalyst bead having the same diameter of the sphere, and that circular image of a circular sphere is a circular, say you are putting light on a ball, and the image which you will get on the screen, it is somewhat a bigger circle because light is diffusing. But we consider that similar diameter circles are there side by side to make a catalyst bed. This way we do the oversimplification, and we can go that there are many folds inside. You cannot do anything very simple, but everything is made simple considering many assumptions in between. Okay. Now, external resistance to mass transfer. We have talked about the external diffusions. Now, this mass transfer or diffusion, how it is posing the resistance. To discuss about the diffusion of reactants from bulk fluid to external surface of the catalyst, we will focus our attention on the flow past a single catalyst pellet. As I have shown the picture previously, similar way we have thought that catalyst, once a single catalyst pellet or catalyst particle is there, and through it, through the outside surface of it, the reactant is flowing. Now, what are the assumptions? Reaction takes place only on the catalyst and not in the fluid surrounding it. It is very obvious. We have considered that without catalyst there is no reaction. So, reaction should take place only on the catalyst and not in the fluid surrounding it. The velocity of the spherical pellet will vary with the position around the sphere. So, fluid velocity is obviously varying because of the fluid boundary layer condition. The hydrodynamic boundary layer, is a concentration boundary layer, is usually defined as the distance from a solid object to where fluid velocity is 99% of the bulk velocity. That means it is considered that on the surface of the catalyst pellet, the concentration is lowest, and as you go just opposite direction, as you go from the catalyst surface towards the bulk, the concentration increases through the hydrodynamic boundary layer, as it is there for the fluid dynamics. For this, as we consider the velocity increases as you go from the stagnant plate or body up to the point where the velocity gains the same velocity as the bulk velocity. That means almost 99% of the velocity. The similar way we consider the concentration boundary layer. Similarly, the mass transfer boundary layer thickness delta is defined as the distance from a solid object where the concentration of the diffusing species reaches 99% of the bulk concentration. This way we have taken the delta thickness. You have just asked about the thickness of delta, no? So, this way we can measure. Now, see, this is the just I have shown, this is the catalyst pellet, and CAB is the bulk concentration, CAS is the concentration on the catalyst surface, and this way this is the boundary layer, oval type. And here you see if it is a y-axis, and if this is y is equal to 0 and this is y is equal to delta, the concentration, this is the boundary layer and this is the concentration decrease. CAB is coming at the CAS with, this is the minimum concentration at y is equal to 0. The representation of the concentration profile for a reactant A diffusing to the external surface is shown in figure. The change in the concentration of A from CaB to CaS takes place in a very narrow fluid layer next to the surface of the sphere. This layer delta is very small. Nearly all of the resistances to mass transfer is found in this layer. So almost all the resistance to mass transfer resides in the delta thickness. Okay. So let me go to next slide. Now, mass transfer coefficient. We consider a fluid layer of stagnant film of thickness delta around the solid particle. It is also considered that all the resistance to mass transfer is limited at this film and the properties, that is concentration, temperature, etc., are the same at the outer edge of the film as the bulk fluid. So this thickness delta is acting as the boundary layer where actually concentrations are continuously going down as you are approaching towards the catalyst surface. Otherwise, just after this delta, whatever concentration is there in the bulk is the same at the outer surface of the delta. And curvature effect is neglected. We have considered no curvature. So one dimensional diffusion equation will be solved. We can take one single coordinate. For either dilute solution or EMCD, that means where there is no bulk flow, we don't go for this one stagnant film. The mass flux at a single point can be written as, say, at a single point in the thickness delta, we can write the flux as, someone has written something, just a moment. It is your, okay, no, it is not here, leave it. So we have taken the single point mass flux. How we can express it? WAP, P means 1 point, DAB by delta tilde into CAB minus CAS, where WAP is the flux at a specific point or portion of the sphere around the boundary layer of thickness delta. This delta tilde is the thickness at that single point. Now the ratio of diffusivity to the layer thickness is the mass transfer coefficient Kc. This one, diffusivity by layer thickness delta tilde is the mass transfer coefficient Kc at that single point, where CAB is the concentration in the bulk and CAS is the concentration on the catalyst surface in that thickness portion, and WAP is also at that point. Therefore, DAB by delta tilde is Kc tilde. Kc tilde is the local mass transfer coefficient at a particular point, the point which we have considered. Now, we have to get the whole total mass transfer coefficient for the whole surface area of the catalyst pellet, gives the average mass transfer coefficient for the area A. So, Kc is equal to integration of Kc tilde dA by A for the whole area A around the catalyst surface. So, average molar flux from the bulk fluid to the surface is WA is equal to Kc CAB minus CAS. The same way, instead of DAB by delta, we have solved it by mass transfer coefficient. So this is the equation WA is equal to Kc CAB minus CAS. As for heat transfer, we have the equation, you know, you have read the heat transfer in your previous class, that QR is the heat flux, is equal to H into T0 minus Ts. This is the temperature gradient. H is the heat transfer coefficient. So we can write the Nusselt number and Reynolds number as Nusselt number HD by KT. KT is the thermal conductivity. H is the H is the heat transfer coefficient, and then D is the particle size or particle diameter, and RE Reynolds number du rho by mu. And Prandtl number is defined as PR is equal to Cp mu by Kt is equal to mu by rho Cp by Kt. This way we can express. Now mu by rho is nu is the kinematic viscosity, and rho Cp by Kt, this quantity, actually Kt by rho Cp is alpha T, which is called thermal diffusivity. So gamma by alpha T is kinematic viscosity by thermal diffusivity. This we can write in similar way, that momentum diffusivity by thermal diffusivity, both are meter square per second by meter square per second. So Prandtl number is a dimensionless quantity. All these are for heat transfer. Similarly, afterwards I'm coming. The relation between Nusselt number and Prandtl number and Reynolds number, this way we can express Nusselt number is equal to 2 plus 0.6 Reynolds to the power half, Prandtl to the power 1/3. And for stagnant film, Reynolds number is equal to 0 if we consider, then Nusselt number is coming as 2. This next quantity is coming as 0. For higher Reynolds number, in which boundary layer is laminar, if boundary layer is laminar, then some Reynolds number is obviously there. So in that case, this quantity, next quantity is much more than 2. Then we can neglect 2 and we can write Nusselt number is equal to 0.6 Reynolds to the power half, Prandtl to the power 1/3. So these way we can write the analogical equations for different non-dimensional quantities. To draw the analogy between the heat and mass transfer, we can write Nusselt number is analogous to Sherwood number and Prandtl number is analogous to Schmidt number. If we do that, then what is coming? Look, why we have taken the analogy between these two numbers. Sherwood number is KCD by DAB. And Kc is meter per second. This is mass transfer coefficient. D is the diameter of the catalyst pellet. DAB is the diffusivity. So if you see this, it is coming dimensionless, and Nusselt number is HD by KT. So if you consider Sherwood number is analogous to Nusselt number, then it can be said that H, this heat transfer coefficient, is analogous to Kc, mass transfer coefficient, and which is also analogous, and Kt is analogous to DAB. Instead of Kt, we can write DAB, diffusivity. Look, this equation also, Qz is equal to H T minus Ts, and Waz is equal to Kc Ca minus Cas. So from here also we can write H is analogous to Kc. Again, Prandtl number is gamma by delta T, alpha T, sorry, gamma by alpha T, and Schmidt number is gamma by DAB. So here again, this alpha T, momentum diffusivity, is analogous to diffusivity, mass transfer diffusivity. Both are dimensionless, so we can write. Therefore, the correlation between Schmidt number and Sherwood number is written as Sherwood number is equal to 2 plus 0.6 Reynolds to the power half, Schmidt to the power 1/3. This relationship refers to Frostlink correlation. This one is said as Frostlink correlation. Look, if we have a stagnant film, then Reynolds number is 0, then Sherwood number will be 2. But if there is laminar flow, then there should be a Reynolds number value. Then we can neglect 2. Then Sherwood number will be 0.6 Reynolds to the power half, Smith to the power 1/3. Mass transfer to a single particle. Here we don't consider the whole bed of catalyst particle. Let us consider only a single particle. So in that case, we have to consider two you can say phenomenon. One is the diffusion, another one is the reaction on the catalyst. In that case, there may be two situations. One is two limiting cases. One is the reaction is so rapid that the rate of diffusion to the surface limits the reaction rate. Once the reactant molecule reaches on the surface of the catalyst particle by diffusion, if it consumes then and there, as soon as the molecule comes on the catalyst surface, and then and there it can react and produce the product, then what will happen? Reaction rate is very rapid, but diffusion is not that rapid. So what will happen? Diffusion will limit the whole process. Diffusion will control the whole process. So in this case, diffusion is the controlling step and reaction is rapid step. So rate controlling step will be the diffusion, external diffusion. Another situation may be reaction is so slow compared to the rate of diffusion that almost no concentration gradient exists between the bulk and the surface, and reaction is the limiting step. So diffusion is rapid, but the rate at which the diffusion is diffusion is occurring, in that rate or more than that rate, reaction cannot occur. Reaction is slow. So there is some accumulation of reactant molecule on the surface, which the molecules which are waiting for the reaction to carry out. So what will happen? It may happen the concentration on the bulk CAB may be almost equal to the concentration on the surface of the catalyst. So the difference in concentration or concentration gradient is negligible in that case. Then what will happen? The reaction is the slow step. So between the diffusion and the reaction is the controlling step. So these are the two types or two situations, two conditions may occur when we consider the external mass transfer. Here one problem is given: rapid reaction on a catalyst surface. When reaction is rapid and diffusion is slow, then diffusion is the controlling step. What is the problem? Calculate the mass flux of reactant A to a single catalyst pellet 1 centimeter in diameter, suspended in a large body of liquid. So what happens? Here mass flux of reactant A, mass flux or mole flux, whatever, reactant A is to be calculated to a single catalyst pellet, which is coming to a single catalyst pellet. Pellet is 1 centimeter in diameter and suspended in a large body of liquid. The reactant is present in dilute concentration, and the reaction is instantaneous on the catalyst surface. That means very rapid reaction. As soon as A reaches on the catalyst surface, the reaction occurs. That means that is CAS is equal to 0. Concentration on the surface at any time is observed as 0, because as soon as it is reaching on the surface, it is getting reacted. The bulk concentration of the reactant is 1 molar and liquid velocity is equal to 0.1 meter per second. The kinematic viscosity 0.5 centistokes. 1 centistokes is equal to 10 to the power minus 6 meter square per second. This is given because to match the units of other units, and liquid diffusivity of A is 10 to the power minus 10 meter square per second. These are the data given. How we can solve this? Look, it is a dilute concentration, so there is no bulk motion, only the diffusional motion. So WA is equal to Kc CAB minus CAS. Now we have to calculate WA. That is the ultimate. It is asked the mass flux or molar flux. This one we have to calculate, and from this equation Kc we do not know. Kc value is not given. CAB value is given 1 molar. 1 molar is 1 mole per decimeter cube. That is 10 to the power 3 mole per meter cube. And CAS is 0. As soon as A is reaching on the surface, it is reacting. So CAS 0. So here it is coming WA is equal to Kc into CAB. CAS 0. Now we can calculate Kc from the Frost-Link correlation. Sherwood number, what is Sherwood number? That is Kc d by dAb is equal to 2 plus 0.6 Reynolds to the power half Smith to the power 1/3. Here, as flow rate is given, we can calculate the Reynolds number du rho by mu or du by nu. Nu kinematic viscosity value is given. What is that? 0.5 cp centistoke. 1 centistoke 10 to the power minus 6 meter square per second. That means 0.5 into 10 to the power minus 6 meter square per second. This one, put the value of nu here. D is particle diameter, 1 centimeter, convert it into meter, so 0.01 meter. U is the velocity. Velocity is 0.1 meter per second, so it is coming as 0.1. So it is coming, Reynolds number is 2000. And so what is the Smith number? Smith number also we have to calculate here. Smith number is equal to nu by dAb. Both are given. Nu is 0.5 10 to the minus 6 and dAb is 10 to the minus 10. It is given. dAb is 10 to the power minus 10 meter square per second. So Smith is 5000. So we can get the Sherwood number. Sherwood number is a 2 plus 0.6 Reynolds to the power half. Reynolds is 2000. Smith to the power 1/3 5000. 460.7. Now from this we know the value of Sherwood number. And what is Sherwood number? This is Kc d by dAb. Now here we do not know Kc. We have to find out Kc. D we know, dAb we know. So Kc is equal to dAb Sherwood by d. It is coming as 4.61 10 to the minus 6 meter per second. Now put it here. WA is equal to Kc CAB. We can get the WA 4.61 10 to the minus 3 mole per meter square second. How many slides I have? Okay, I am stopping here today. We have class on Friday, but Friday is the exam. Exam will be of maximum 40 minutes and exam will be of maximum 40 minutes, maybe 15 to 20 marks. Within that 40 minutes, you have to upload your pages, screenshots, and don't submit in email. Email submission will not be entertained. Okay, this is the thing. I'll write everything in email. Okay, and so best wishes.
Ma'am, whatever you taught today will going to come into
No. Look, everything I'll write. I have to make the question. No, I haven't made the question. Today I'll do it and write you by email. Okay.
Okay, ma'am.
But it will be evening because I have class in the afternoon. Again, I have a meeting in the evening. It may take some evening time. But you start study. Hopefully, you have started already. You do solve that assignment. Chalo. I'm leaving.